Welcome back. Today we're going to talk about reaction pathways and reaction mechanisms. First thing we have to talk about is called a heat content diagram. As we're talking about heat content diagrams, remember that activation energy, something that we introduced last time, is the minimum amount of energy required for a reaction to even occur. So a heat content diagram has the activation energy included on it, but it represents this through potential energy. This is different than when we were doing the kinetic energy distribution curve, which uses kinetic energy. So let's check it out. Let's first draw a heat content diagram for something that's exothermic. So we're going to slap down a couple axes here. And on the y-axis, we're going to put potential energy. And on the x-axis, we're going to put reaction progress. In the book, they say time, but I think reaction progress is definitely the better thing to list here. Now, this is an exothermic reaction, which means I'm going to be releasing heat, right? So I want to start with my reactants kind of high, and I have this sort of lump like this, and then it goes down, and that forms products. So let's label these. So this is the reactants here, and this is the products here. And here's something else that we can label. We can label the amount of energy that's involved. This is the energy given off by the reactants, and remember that H can be used to represent energy, and this is the energy used by, or that the products have at the end of the reaction. And if I wanted to find out the overall reaction energy, I would probably want to just find the difference between these two values, the change. And that change would be calculated with something like the heat of the products, or the energy of the products minus the energy of the reactants. That would give me the overall change, and in this case, it's going to be probably a number that's negative, which makes sense, right? Because we have lower energy in the products and higher energy in the reactants. This is exothermic after all, so that energy released is energy that's going into the system. And just like we were talking about before, each reaction has a minimum amount of energy required for that reaction to start. Where do you think that energy is on this particular graph? Well, it's probably here, right? Like this lump is probably what we call the activation energy. That's the energy required for the reaction to even occur. We need to get over that activation energy before we can even start. So even though this is exothermic, this reaction requires energy to start. So energy has to go in, even though the net gain or net loss of energy is released. So even though it's exothermic, that doesn't mean it's all just release. There is some absorbing happening here, but overall, it's release. Let's think of something else too. You can add this here if you'd like, but what if we draw another graph that looks something like this, and it's aligned with this graph in a very similar way. And this one has an activation energy that's about this tall. Let's see if we can use that to answer this second question. Which of the above figures do you think would be faster, like the first graph or the second graph? Well, I would probably assume that the second graph is the faster one because it has a lower activation energy, which makes it a faster process. We're going to get more into this a little bit later, but remember that the only way that we can really adjust activation energy is by using something called a catalyst. All right, so let's keep going. I'm just going to grab something here. I'm going to duplicate this. I'm going to bring it with me because we're going to now do an exothermic reaction. I'm going to put potential energy over here again, or excuse me, endothermic. Now endothermic means that we're absorbing energy, so we're going to want to start pretty low, and then we rise way up, and then kind of level off. This is the reactants. This is the products. And we can label things just like we did last time, where we have the heat of the reactants here. We have the heat of the products here, or the energy of the products. And the activation energy this time is going to be way bigger. It's going all the way up. That's supposed to be a straight line, buddy. Let's go all the way up. Boop, there we go. And that is the activation energy. Notice a few things. If we were to look at the heat of the reaction like we did last time, we have that delta H value. This time you would probably assume that your delta H is going to be positive, right? Because your products have more energy than your reactants. And we also notice that the activation energy is really, really high. Later we're going to learn that this means that this reaction is what we call non-spontaneous. So we're going to learn that this is non-spontaneous. Now, again, the heat of the reaction is positive, but does that mean that this reaction only absorbs and doesn't release any heat? No, I mean, this part right here, that's a release of heat. So what we're saying is that both endothermic and exothermic both have a time where they have to absorb heat, and they both have time where they release heat. It's just about a net amount. Do I overall absorb or release? It depends on what kind of reaction it is. Now we can take these graphs and we can actually compare them to our heat content diagrams that we drew before. So let's take a heat content, or excuse me, not a heat content diagram, but a kinetic energy distribution curve. What I'm going to do is I'm going to take my kinetic energy distribution curve and I'm going to flip it on its side. And this is kind of weird, but the reason why I'm doing this is because I want kinetic energy to be on this side. Because then I'm going to take this and I'm going to compare it to one of these heat content diagrams that I was drawing before. I'm just going to write reaction on the bottom. And you might want to take your paper here and maybe turn it to the side so you can draw your heat content diagram. And so that's my kinetic energy distribution curve. And let's do exothermic, so something like this. And the big takeaway here is that if you realize the activation energy for the potential energy diagram, the top of the hill, is also the activation energy as determined by the kinetic energy distribution curve. So they're the same. This is just like what we saw last time. That means that everything above that line is particles that have the ability to react. But anything below that line, those are particles that do not have enough energy to collide and form, products. Look at the reactants. Like if we were to follow the reactants along, we would see that the reactants fall in that section that don't have the amount of energy to react immediately. So the reactants need something, they need energy to get going. Even though this is exothermic, those reactants still need a push. And that's kind of the idea. Say, for example, if somebody put a boulder at the bottom of this hill, and it was your job to get that boulder over the hill and down to the products, you couldn't just go up behind the boulder and give it a couple taps and then whoop, up the hill it went and down the hill it goes, right? Instead, you would have to get behind that boulder and you have to push it all the way up. And then once you get it to about here, that's when kinetic energy or potential energy takes over and it all becomes kinetic energy and it rolls down the hill, right? That's all it takes. So the idea is very similar. So now that we have an idea of these graphs, let's talk about mechanisms themselves. A reaction mechanism, first let's consider the top equation that we see there. That top equation is pretty complex, but what it's implying is even more complex. What it's implying is that those four particles in the reactant side, the 1 C2H4Br2 and the 3 I minuses, it's saying that all of them are apparently colliding with each other at the same time, at the right location, and with just enough energy to react into all of those products all at once. Like it's just this thing where they just go bam, and then everything becomes products. And that seems a little unlikely. In fact, it's so unlikely that we would consider it impossible. So instead, what we have to do is we have to take a reaction like that and break it into what's called elementary processes. Little steps. And all that takes is that we say we take one thing at a time, actually two things at a time, we just kind of smash them into each other in small little steps. And that's actually how chemical reactions occur. We can prove this with a little more science, but that's not really that important. Let's write out the mechanism for this and let's see if we can explore it. Now I'm going to write about 5 lines of chemical reactions, so if you want to make yourself space, make sure you have space for like 5 lines. So let's get started. We're going to take that C2H4Br2 and we're going to react it with only one of those I minuses. And those are going to collide. And one of the bromines is going to pop off and we're going to get IBr. And now we're going to take that IBr that we just formed. Oh, excuse me, not yet. I'm getting ahead of myself. Then we're going to take that C2H4Br minus that we just formed. And we're going to break it apart into simpler components. We're going to break it apart into C2H4 and Br minus, which we're going to use later. Now let's go back to that IBr. We're going to make that react with another one of our I minuses from the beginning, and that's going to give us I2 and Br minus. And then we're going to take that I2 that we just made, and we're going to hit it with another I minus from the beginning. And we are going to form I3 minus. Now, this seems like a lot. And I want you to understand that there's never going to be really a situation where you have to write this by yourself. Instead, what you're going to have to do is just interpret information from this. A lot of times these are going to be labeled, so you might remember this from when we did the clock reaction lab. There was a reaction mechanism at the front. Your clock reaction lab did not have something like this, however, which many things often do, where it tells you the rate of the reactions on the side. And we'll talk about that in just a second. But one of the things that we can do using this mechanism is we can write the overall reaction. So this is very similar to something like maybe you've seen in math, where we're going to take this reaction and we're just going to remove things that are the same on both sides of the arrow. It's like simplifying. And we've kind of done this in the past when we did net ionic equations. But let's see if we can find stuff. So say, for example, like IBr and IBr, those are the same on both sides. C2H4Br minus, C2H4Br minus, those are the same on both sides. What else? I2, oh, my circle got a little scratch there, and I2. Those are both the same on both sides. So now we're going to take everything that's left over and we're just going to drop it down. C2H4Br2, 3 of those I minuses. Little arrow. Got the C2H4, 2 of those Brs, and 1 I minus. And that's it. So I've seen that equation before. Where's that equation from? Oh, well, it's from the beginning. Yeah, it's right there. So we got back to the original reaction, which is good. That means we did something right. Now, there's a lot of reasons that we do this. One of the reasons is that it helps us break down the reaction and we can see what's going on. Another reason is it helps us see what step of the reaction is fast. Another one is that we can identify things called intermediates. So let's fill in a couple blanks and then kind of bounce back and forth. Each step in these reactions is going to lead to the next step. So if you notice, I always form some sort of product and then use those products later. Things aren't just coming out of nowhere, they are coming from somewhere. The sum of all the individual steps will give us the overall equation. That's the thing that we did together. And then the slowest step in the mechanism is going to govern the rate of the overall progress. The old saying is that a chain is only as strong as its weakest link. It's about the same in chemistry. A chemical reaction is only as fast as its slowest step. We can increase the rate of those other 3 steps, but until we increase the rate of the slow step, we're really not going to make much of a difference in the overall rate of the reaction. That's the one that we have to focus on if we want to actually change the rate of the reaction. So again, that's why we have to label those on the side, because it'll tell us which one is the slow step. All right. We can also determine things called intermediates. Intermediates are these unstable, short-lived particles. They collide and they're formed and then they're broken apart. And that's how we can identify them. In a mechanism, they're going to form as products, exist very briefly, and then they're going to fall apart as reactants. And then they should just disappear as far as the overall reaction. They should never actually be involved in the overall reaction. So why don't you take a second, go and look in that chemical reaction that we did together and see if you can find which of those are the intermediates or the activated complexes. Understand that they are interchangeable terms. So another term for this is activated complex. Activated complex. So again, go and see if those, if you can find which ones are the intermediates. I'll give you a hint. They're the ones we circled. So that should be C2H4, Br minus. It should be IBr, and it should be I2. And let's see if those fit the criteria that we established before. They are formed as products, which looks good to me, and then they are used up later as reactants. Yeah, I could see that, right? This is formed here, it's used there. This is formed here, it's used there. This is formed here, and it's used there. So again, formed as products, used again as reactants. So let's keep going. We can relate these activated complexes, and we can also relate them to heat content diagrams, right? So an activated complex, again, is just something that exists in a moment of contact. It's very brief, it's very unstable. If we were to draw another one of our heat content diagrams, I'm going to do this one kind of sloppy. So feel free to do yours kind of sloppy too. We're going to draw another heat content diagrams. Those are the reactants, those are the products. Potential energy over here, reaction over there. Where do you think the activated complexes would exist? Well, we want to find a place that is high energy and doesn't last for very long. I would say that would be here at the top of the lump, right? The reactants collide with each other with a lot of energy. They exist as those activated complexes very briefly, and then they break apart. And this is a very, very, very simple breakdown of this process. If I had something a little more complicated, like let's say that I drew another graph that had multiple intermediates, kind of like what we saw in our example, my graph would kind of look a little bit more like this. And this is where we would form those activated complexes. There'd probably be intermediates in the middle here, activated complexes, and then these would be reactants and these would be products. And depending on the number of steps, you might have a lot of lumps, going up or down. They could go up and then back down and then up and down. So again, this can get really complicated, but understand that for the most part, this is the kind of graph that we're going to be focusing on. We're not really going to be getting too much into it with those other types of graphs. Now again, it's just really important, so it keeps being restated here in the notes. An activated complex is highly unstable and it's short-lived, so it's not really something that's going to exist as product. It just shows up and then it goes away. Now we can also relate these two concepts, both the heat content diagrams and the mechanisms, back to catalysts. Remember that catalysts are able to speed up an overall reaction by lowering the required activation energy. It's the only thing that can lower the activation energy. So if we reconsider our heat content diagram, and we kind of drew this before, so let's kind of draw it again. Oh, that's real bad. Well, if we were to draw another heat content diagram, where we have the reactants and we have the products, and we were to label the activation energy for this, we would label this as the activation energy, and let's just say this is an uncatalyzed reaction. If we were to draw a catalyzed reaction, we would have a very similar line, but we would notice that the reaction has a much smaller activation energy, right? And this would be the activation energy if it was catalyzed. Just like we saw before. So again, what it's doing is it's reducing that required amount of energy, which speeds up the overall reaction. Let's see if we can compare this to our heat content diagram and kinetic energy distribution curve. Take a second and draw these back out again. I'm just going to kind of pause and draw them so I don't make you watch me draw the whole thing. All right, so I just kind of copied mine from before, and now I'm going to adjust my activation energy for my new graph. So this is now my activation energy if I was catalyzed. And now let's label this one as uncatalyzed. Uncatalyzed. There we go. We draw our line across, just like we did before. Straight line. And now you might notice that we are again increasing the number of particles that can overcome that threshold and react. So there's something that I want you to keep in mind though with both of these graphs. Do you notice that with both the kinetic energy distribution curve and with the heat content diagram, the overall energy related in the reaction does not change? The delta H. The delta H for this reaction is not affected. It is the same for both. It's really important for you to keep that in mind, that the catalyst has nothing to do with the overall energy involved in the reaction. So how do we recognize a catalyst in, let's say, a mechanism? It's a little different than an intermediate, but the idea is kind of the same. The catalyst is going to show up as a reactant, and then it's going to be canceled out way later as a product. So it shows up in the beginning as a reactant, leaves later as a product. And let's see how that works. Well, let's actually just kind of go over the whole thing. So I want you to take a second and practice this a little bit. See if you can identify all the intermediates and the catalyst and write the overall reaction for this reaction here. Go on, pause, give it a try, and then come on back when you're done. All right. So let's identify the intermediates first. So remember that an intermediate is something that shows up as a product and is later used up as a reactant. So I would say I is one of those things because it's used up here. Ooh, actually I got two of them. So I would say I spelled intermediates wrong. How embarrassing. Intermediates. There you go. So I is one of them. Let's see, what else? Cu is one of them. Formed as a product, used up as a reactant. Now be careful, this is Cu plus. CuSO4 is another one. And I'm just going to write that one below. CuSO4 plus. Now let's see if we can find the catalyst. The catalyst is something that is used as a reactant and then comes out later as a product. So I have Cu plus 2 here, which starts as a reactant, and then at the end of the reaction, it comes out as a product. So I would say that is the catalyst. Everything left over, those are the things that we are going to drop down and we are going to use in our overall reaction. So that's S2O8, 2I, and we also have I2 and SO4 minus 2. My pluses and minuses are sloppy. Let's fix those. Oh, that's not any better. Boom. And that's it. So that's how we would identify a catalyst. Again, shows up as a reactant, used up as a product. And that is reaction mechanisms. Thanks for sticking in there. I know this was a long one. We'll see you next time.